All right, so what we're going to look at now is confidence intervals, and we're looking at this for proportions. So what we have here is we have a population here, and this is what P is right here. This is the proportion of successes in the population is 0.5, and we're sampling 100, sample size of 100 people. So we're going to take a sample, and what we get is that our p hat, or our successes in the sample, the proportion of successes, is 47%. Okay, so we do another sample, and now in the second sample our proportion of success is 0.51. All right, so what we talked about in the last chapter when we're doing sample distributions for proportions was that the mean of our sample distribution, if I was to do, let's do 100 samples of 100. So that's what our sample distribution looks like. And in our sample distribution, the mean of our sample distribution is going to be approximately what the mean of our population is. But if you look here in all of these different samples, okay, not all of them are around 0.5. You have some in here that were just below 0.48. Looks like it was the most common one. Okay, so we pulled all of these different samples from this population, and any one of these could be the sample that we were working with. Okay, so like we look over here, this looks like this is around 0.39. We could have pulled a sample that was 39% from a population that had a proportion of 50% successes. Okay, or we could have pulled this over here, which is probably around 0.6, and that would have been a p hat of 0.6 from a population that has a proportion of 0.5. Okay, so even though when we pull a sample from our population, we know it's going to be a pretty good approximation, we also know that there's going to be variation from sample to sample. So in here we have 100 different samples. Okay, and not all of them came out to be exactly the same. Okay, now we know that they should be good approximations if we do our sampling techniques correctly. But we also know that it's probably unlikely that our p hat is exactly what p equals. Okay, so we're going to do what we call an interval, and basically over here these are a bunch of intervals, and where these black dots are, that's where the p hats landed. Okay, so what we had to do is we had to say, okay, we have our p hat, but we have to account for the variation from sample to sample. So if we pull a p hat, we're not going to say, okay, we got a p hat of 0.47, so that's what p should be. Well, no, we're going to say, okay, we pulled a p hat of 0.47, that's probably around where p is, so p could be up above that, like 0.50, or it could be below that, maybe 0.44, but it's somewhere in there. Okay, we don't know exactly what p is. Okay, when we do these intervals, remember, when we're doing sampling, a lot of times we don't know what p is, and a lot of times p is unknowable. So we had to account for the fact that when we're doing our sampling, we don't know that, and when we sample, we're going to get variation from sample to sample. So we're going to create a fudge factor that's called an interval, and that's basically what we're going to look into in this chapter. Alright, so let's look at inference for proportions. So in our population we have what we call parameters. Okay, and in general those parameters are going to be P for proportion, so that's the proportion of people that are Democrats. Okay, or we could be dealing, if we're dealing with means, we would be dealing with mu. And mu is the mean IQ score of all males in the United States. Okay. So generally parameters are unknown, and in many cases they're not knowable. Okay, so when we do inference in general, we're not going to know what P is, and we're not going to know what mu is. So in this chapter and for this unit, we're going to be concentrating on P, okay, which we're dealing with proportions. Well, from our population, we do a sample. And in our sample, we get what we call statistics. So if we're doing a proportion, we get P hat. And if we're doing a mean, we get X bar. And by the way, what would be paired with mu would be the standard deviation. And what would be paired with X bar is S, which is the sample standard deviation. Okay. So these are statistics. Okay, statistics are born from a population. Okay. And they're good estimators of what the parameters are. Okay. But what else our sample brings into account is variation, because there's going to be variation from sample to sample. Every sample that we do is not going to have the same P hat. Okay, we expect it to be a good approximation of P. Okay, but we know from sample to sample we're going to get what we call sampling error, which is the natural variation that occurs from sample to sample. Same thing with X bar. X bar is going to be a good estimate of mu, but every sample that we do is not going to have the same X bar. Okay, so we have to take into account that we're going to get variation, called sampling error, from sample to sample. So that is the whole concept of inference. Now, we then take this sample, okay, and then we infer something about the population. Okay. The majority of people who live in the East and the West are Democrat. Okay. The majority of people who live in the South are conservative, Republican. Okay. So these are the kind of inferences we can make. Okay. So what we've looked at is that when we do a sample distribution, we know that the standard deviation of a sample distribution for P hat is going to be the square root of PQ over N. Right. However, we hardly ever will know what P and Q are. Okay, we can hypothesize what we think P is, and we'll get into that in the next chapter. Okay, but that doesn't mean we know what P is. So we're generally going to be dealing with P hat and Q hat. Well, if we're dealing with P hat and Q hat, then we're dealing with statistics. And we no longer call it standard deviation. We now call that standard error. Okay, so now the standard error is when we know what P hat and Q hat are, but we don't know what P and Q are. So a confidence interval, what we're going to start with is we're going to start with P hat. And assuming that we meet our success-failure condition, we know that our sampling distribution is going to be roughly unimodal and symmetric, or fairly normally distributed. And based on where that is, we're going to create an interval based on a normal model. So we're going to say, okay, this is where we know that p hat is. P hat's always going to be here. We're going to say that we're going to create an interval to capture p. Okay? Now, if I do I'll do just a couple of intervals here. If I do a 90% confidence interval, then that means I'm capturing 90% of this distribution based upon where p hat is. So that means that if I'm doing a 90% confidence interval, that means that I'm starting at the 5th percentile and I'm ending at the 95th percentile. Okay. Well, if we go into our calculator and we say, okay, calculator, I need a z-score for that, we go into inverse norm and we say, okay, calculator, give me a z-score for the 5th percentile. It's negative 1.645. Well, give me a z-score for the 95th percentile. Well, it's positive 1.645. Why? Because they're equidistant from the mean, which is p hat right now. Okay. If I do a little wider interval, so now p hat's in the middle of my sampling distribution, I'm going to do a wider interval. 95% confidence interval. Well, if I'm capturing the middle 95%, then that must mean that I'm not capturing 5% of the interval. That means if I'm not capturing 5% of the interval, I'm going to split that 5% equally. So that must mean I'm not capturing this 2.5%. So that means to me that this percentile is the 2.5 percentile, and I'm not capturing this 2.5% over here. So that must mean that this interval goes to the 97.5%. Okay. So I go to my calculator and I say, okay, calculator, what's the z-score for that? And it's 1.96. Okay, well, if this is a z-score of 1.96, then this must be z equals negative 1.96. And then this would be z equals 1.645, and this is z equals negative 1.645. So our confidence interval is always going to be our p hat in the middle, and then if we go to the right, we're going to add an interval, and if we go to the left, we're going to subtract an interval, so plus or minus. Now we're going to do how far this interval is going to go. Well, how far is that interval going to go? It's going to go whatever our z-score is times our standard error. Well, what's standard error? Well, we already determined standard error is right there. It's square root of p hat q hat over n. So we're going to do p hat plus or minus z times the square root of p hat q hat over n. Okay. So what do we do at a 95% confidence interval? Well, we do p hat plus or minus 1.96 times the square root of p hat q hat over n. That 1.96 will always be the same for a 95% confidence interval for a sampling distribution for a proportion, because that sampling distribution for a proportion is normally distributed, and 1.96 standard deviations from the mean always brings me to the 97.5th percentile every single time. And in a 90% confidence interval, we do p hat plus or minus 1.645 times p hat q hat over n. Well, why? Because our sampling distribution is going to be normally distributed as long as it meets our success-failure condition. And every time I go 1.645 standard deviations from the mean, either way, that brings me either to the 5th percentile or the 95th percentile. Okay? Alright, so, key point. When we do a confidence interval, not only is P unknown, but in almost every case, it is unknowable. We've already talked about that. Now, we talked about conditions in our last chapter, okay? And I'm just going to put these generally for now. There's going to be 3 sampling conditions generally. And the first condition is your sample must be random or representative. You must have a random or representative sample. Okay, the second one is that you must be sampling less than 10% of the population because you're sampling without replacement. And if you sample more than that, then you significantly can change the p-value that's left in your population because of the fact that you're sampling without replacement. The third condition is some kind of independence. Now that independence will depend on what kind of inference we're doing. It's either that the subjects are independent or that the samples are independent, but you'll always have some kind of independence condition. Okay? And this is whether we're dealing with a proportion or a mean. We're dealing with p or mu. It doesn't change. Now what will change is this fourth condition. And we must always have some condition that allows us to use a normal model. Well, we've already discovered this, right? We talked about this back in chapter 17. We said, oh, we have that. It's that NP is at least 10 and that NQ is at least 10. Well, hold on, Mr. O'Neill. You said that P is generally unknown and unknowable. So we're not going to have P and Q most of the time. You're right, not unless we hypothesize it. So if we don't have P and Q, we use the next best thing available, P hat and Q hat. Okay, so those are going to be our conditions when we're dealing with means and proportions. Okay, going forward, we're always going to use those more setting up our inference procedures. All right, so whenever we do an inference procedure, this is going to be our blueprint, and this makes sure that we cover all of the bases when we answer a question. Okay, so I come up with this acronym. It's actually, yeah, it's an acronym. Phantoms. I'm not sure I didn't steal it, but if I stole it, I apologize to anyone if I'm stealing their thunder who's watching this. But basically, here's what we're going to do. Okay. Now, when we do confidence interval, we will not use all of these, but as you go on and you do inference tests, this is going to make sense to you. Okay. It's a nice way to just lay it out and to be able to answer a question in a nice format where you make sure that you touch all the bases. Okay, what P stands for is our parameter. We must identify what our parameter is. So for instance, we're going to have for now we're going to deal with P. So P is the proportion of whatever. proportion of people who smoke, proportion of people who use alcohol, okay, whatever that is. Another parameter that we'll be using is mu. Mu is the mean number of whatever. The mean SAT score in math for all Brian McMahon students. Okay. The mean income level for all people who live in Norwalk. Okay. So our parameter, again, comes from our population. Don't forget, right here, there's your parameters. Okay, for now, it's P if it's a proportion, it's mu if it's a mean. Okay. H, we're going to get into. Okay, but what H stands for is hypothesis. So if you're hypothesizing something, I think that the majority of seniors at Brian McMahon High School use alcohol. So you would have a hypothesis, okay? You would, and I'll show you how to write a hypothesis, okay? But you're hypothesizing something, okay? You're making an educated guess based on either empirical evidence or anecdotal evidence, okay? And then you're going to try to either prove it or disprove it. But we're not going to do that right now. So when we do confidence intervals, we don't got to worry about doing a hypothesis. A is your assumptions and conditions. And I already went over those. There's always 3 for the sample. Your sample must be random or representative. Your sample must be less than 10% of the population. And there's some kind of independence involved. Okay? And then the 4th condition, when we're dealing with proportions or means, is something that allows us to use a normal model. Okay? Or a derivative of the normal model, which we'll get into. N is we got to name the test. Name the test. So what are we doing right now? Well, we're going to do what we call a one proportion confidence interval. So I just like to put that. That's fine. If you put that down on the AP test, that's fine. The people there are statistically minded people, so they know that CI means confidence interval. You'll be okay. Okay. Now, this goes by the name of something else, so it's going to make sense for you in a little bit, and that's called a one proportion zient. What does that mean, Mr. O'Neill? That just happens to be what your calculator calls it. Okay, that's how your calculator doesn't have one proportion confidence interval. Your calculator has a one proportion z interval. That's your calculator. So if you put that down, that's okay. Call it either way. Okay, and we're going to name all the other tests. Okay, so we'll be doing a two proportion confidence interval. We'll be doing a one proportion hypothesis test, two proportion hypothesis test. Then we'll be doing tests for means, and those are no longer called. Those are a slightly different distribution called a t-distribution. So we can call that a one sample t-test, a one sample confidence interval for means. However we want to name it, we'll get there. Okay, but right now this is what we're dealing with. We're dealing with a confidence interval for proportions, so that's what we name the test. T is your test statistics. And parameters. So these, I always call these the players in the game. Who's playing in the game? Well, we're dealing with proportions right now, so we're just going to call these P hat, Q hat, and N. Okay. Now there's going to be other players in the game as we go and we do other tests. So if we hypothesize what P is, then we write down P equals, and then we would write down what Q is. Okay, but right now that's all we need. So P hat is the proportion of successes in our sample, Q hat is the proportion of failures in our sample, and N is our sample size. is we're either going to obtain our interval okay, or we're going to obtain big P. Hold on with this right here. We'll get into this. Okay. You obtain big P when you do a hypothesis test. You're not doing a hypothesis test right now, so don't worry about it. But you are obtaining your interval. So, well, how do you obtain your interval? Well, you have a confidence interval. You know that it equals. Right now, it's your statistic, which is P hat, plus or minus Z times your standard error, which is square root of P hat, Q hat over N. Now Z will depend on what confidence level you're looking at, but that's what we did right here. Okay, so we just got to fill the players in the game into this thing. Okay, so what you need to remember right now is that a 95% confidence interval has a Z of 1.96, and a 90% confidence interval has a Z of 1.645. You're then going to obtain your interval. So what you're going to have is, in your interval, you're going to have a lower bound, and you're going to have an upper bound. Okay? So you would write down what that interval is. M does not obtain to confidence intervals. M this only applies to hypothesis tests. Because here's the deal: if you formulate a hypothesis and you take all of the statistics you have, you must now make a decision. Is your hypothesis correct, yes or no? Okay, so in this case, we got to make a decision. So again, we don't have to make a decision because we didn't formulate a hypothesis. But we do have to do the last part, which is state the conclusion. And this is very important, and make sure you write this down in context of the problem. So if my P is the proportion of seniors at Brian McMahon that smoke, okay, if that's the parameter I'm trying to capture, then when I state my conclusion, I'm going to write my conclusion in terms of the proportion of seniors at Brian McMahon that smoke. I don't just write some general ambiguous conclusion. Okay, it's always got to be in context of the problem. Okay, so this is going to be our blueprint for all the way through chapter 27. We're always going to use this. Okay, we're just going to use different players in the game, and things are going to change a little bit for us, but we always are going to just follow that blueprint in order to answer the question. Alright, so let's do an example here. Your local newspaper polls a random sample of 330 voters, finding 144 who say they will vote yes to the upcoming school budget. Create a 95% confidence interval for all voters in this town. Okay. So P is our parameter, and we're looking obviously here for a percentage of people that are going to vote yes to the upcoming school budget. So our parameter, this P does not stand for our proportion. This P stands for parameter. So you must put the parameter down. Our parameter is P. And P equals the proportion of people who will vote yes to the upcoming school budget. Okay? H is our hypothesis. We're not hypothesizing. Don't need to do that. Okay. A is our assumptions and conditions. Conditions 1, 2, and 3 are about our sample. Do we know if our sample is random or representative? Well, we know it's random. It says it right there. Okay. The sample is random. By the way, it is not acceptable when you're writing down your conditions to just list the condition and put a check mark next to it. So you would say random check mark, independent check mark. No. Okay, you must put the condition again in context of the information that you know. So don't write a one word thing there and then say, oh, or put a yes next to it, or put a smiley face. And that's not acceptable. It's not acceptable on my tests, and it's not going to be acceptable on the AP exam. So it's just very short. You can write this as a narrative if you want. Okay, the sample is random, period. Okay. The next thing would be that the independence. Well, what's independent? Each voter. So I would say that each voter is independent. We have 330 people in our sample. Okay, so that means that it has to be less than 3,300. Okay, if we meet the 10% condition, well, most towns are more than 3,300. So we'll assume that 330 is less than 10% of all voters. Now the fourth thing is what allows us to use the normal model. Well, we're dealing with proportions, so you got to use NP. Well, you don't know what P is. The next best thing, what's NP hat? What's the number of successes in the sample? Well, it's pretty simple. It's 144. So NP hat equals 144, and that's at least 10. Well, what's NQ hat going to be? Well, it's going to be 330 minus 144. So that's going to be 186. And that's at least 10. Okay. So we're okay to use a normal model. Okay. Again, on this, you cannot just do this. NP hat is at least 10. NQ hat is at least 10. Good to go. No, you must show why it's at least 10. You got to show the math here. Okay. Even though we didn't have to do any calculations here. All right. Name the test. This is a one proportion confidence interval. Who are the players in the game? The test statistics and parameters. P hat is going to be 144 over 330. That's the number of successes. So it's 0.436. Q hat is going to be 0.564. And N is 330. Now we got to obtain our interval. Okay. So our confidence interval equals our statistic P hat plus or minus, in this case Z for a 95% confidence interval. Remember what it was? 95% confidence interval was 1.96. That's this guy right here, right? I see I made a mistake there. That should be not negative 0.196. That should be 1.96. Okay, so 1.96 times our standard error, which is 0.436 times 0.564 Q hat over N. Okay, so if I was to calculate this out, I would probably calculate this first So let's do that. Let's do the square root, and then we'll do open parentheses 0.436 times 0.564, close parentheses, divided by 330, because that whole thing is under the square root, and then I'm going to multiply that times 1.96. So it's 0.0535. So my confidence interval is going to be 0.436 plus or minus 0.0535. So I do 0.436 minus 0.0535, and that's 0.3825. So that's my lower bound because I subtracted. And now I'm going to do 0.436 plus 0.0535, and that's 0.4895. So, based on this, what do we know? Well, what do we think is pretty likely to happen? Okay, well, what we know is we're 95% confident that P is somewhere in this interval. So that's the actual proportion of people in the entire town that are going to vote yes to the upcoming school budget. So, since our entire interval is under 50%, we're pretty confident that the new school budget is going to get rejected, because less than half the people are going to vote for it. Okay. So, we don't have to make a decision because we didn't hypothesize anything. Oh, let me show you one other thing. All right, now when you do these, you have to put this down. This has to go down, but we don't have to calculate it by hand. Okay, so go to your calculator, and you're going to go. Let's see, stat tests. Okay, and you're going to go to one prop zient. Let's see where that is. There it is. Now you see this one here where it says, I just went by it, Z interval, don't go to that one. One prop zient. There it is. Now in this, you have some different variables. What X is X is the number of successes. So in this case, we know it's 144. Okay. X always must be a whole number. If you put a decimal in this, because if you're counting the number of successes in a sample, you can never have a decimal. Okay, so that's what we call a discrete variable. Okay, we talked about that in the last unit. Okay, you cannot have decimals and fractions as to your number of successes. It's impossible. N is your sample size. So we go and we calculate that, and there's our interval, 0.383 to 0.489. Okay, so yes, this is a little bit different, but that's because we rounded. And there it gives us our p hat also. Okay, so we can just go to one prop z in and let the calculator do the actual calculation for us. However, this must still go on our paper. So this has to go on our paper, and this has to go on our paper. Now, what is our conclusion? Well, we are 95% confident that between 38.25% and 48.95% of voters in this town, that's what we're talking about, whatever town it is, will vote yes to the upcoming school budget. So we're 95% confident that P is somewhere in here. Okay? Because this is our approximation P hat. And we know that that's going to be somewhere around P. We know it's probably not going to be exactly on P. Okay? So what would happen if we did a 90% confidence interval? Well, we would just take this formula, our confidence interval formula, and instead of 1.96, we would use 1.645. Okay? And I am going to do this out because I want to show you something. Okay. So again, I'm going to do the same kind of thing that I did, in that I'm going to do the square root of 0.436 times 0.564, close parentheses, divided by 330, and then I'm going to multiply that by 1.645, and that's 0.04, let's round it to 0.045. So this is 0.436 plus or minus 0.045. This is 0.436 plus or minus 0.0535. So what happens here? Your interval is going to be narrower. Okay, you're going to have a smaller interval, hence you're less confident. Okay? So you're not as confident, okay, but you have a narrower interval. Okay, so what we're trying to do here is we're trying to be a little bit more precise. But when we try to be more precise, we try to narrow down where P is, okay, then we wind up losing confidence. Now I can be 100% confident, though it'd be useless. If I'm dealing with a proportion, I can be 100% confident that the proportion of voters who are going to vote yes in the upcoming election is between 0 and 100%. But that's useless for us. Okay, so we're never going to be 100% confident. So again, I'm going to go into my calculator now, and I'm just going to go to stat test, and I'm going to go down to 1 prop z int. And I'm just going to let the calculator, the only thing I got to change is I'm going to change that to 90%, and then I'm just going to let the calculator calculate it. Now I'm between 39.1 and 48.1. So this is 0.391 and 0.481. So what does that mean? Well, now we are 90% confident that the proportion of voters in this town that will vote yes to the upcoming school budget is between 39.1% and 48.1%. I worded it a little bit differently, but that's basically what it means. All right, so that's our first example of a confidence interval. All right, so we have an applet here, and in our applet, there we go. We have some marbles, and we're looking at the orange marbles. So the proportion of orange marbles in our applet is 49%, and we're going to do a 90% confidence interval with a sample size of 50. In our first sample, we got 48%, so that's a pretty good approximation of 49%. And then we made an interval, and you'll notice in our interval, that this red line represents the 49%. We captured our p-value. Our second sample, we got a p-hat of 44%, which is 5% away from our p-value. Okay, a decent approximation, but again, we created an interval, and in our interval, we captured our p-value. Okay. Then we got 44%. This one we got 54%. So we created an interval based on 54%. Now what you notice is these intervals are pretty much the same size. Okay, it's just that the middle of them is wherever our p hat is. Okay, now that one barely captured our p-value. Now notice the sample p-value, p hat, I'm sorry, is 60%, but the actual p is 49%. So that's not a great approximation. That's 11% away. But again, what you're noticing is when we're doing samples, we're getting variation from sample to sample. Okay, but when we create our interval went down to, let's see here, looks like just maybe 48%. So our p-value is just barely in our interval. Okay, and then we got 56% for p hat, and then 50%, that's a good approximation. 50% again, 56%, 50%, 42%, 42%, 58%, 52%, 52% again, 58%, okay, 38%, 42%, 42%, 52%, so forth and so on. Okay, I'm keep on going because I want something to happen here. Now what you are noticing is variation. Okay, there we go. There's the one we got. Okay, so we did a sample, we did a random sample, or we did everything correct. But what happened here? Well, in this sample, we created an interval based on a p hat of 64%, and our interval, it looks like, goes down to about 52%, and it goes up to 75%. Okay, it should go equidistant, so I'm not sure. This is, it looks like it's going plus or minus 11%, so it looks like it goes, if I add 11% it'd be 75, if I subtract 11% it'd be 53. Okay, so what happened there? Well, we did everything right, but we didn't capture p. Okay, p is the red line. Okay, that's why we're 90% confident, because we can do everything correctly, but just because of the natural variation that occurs in sampling, we may wind up creating an interval that doesn't actually capture p. Okay, so that's basically what can happen in that situation. Okay, so now what I want to do is I want to go and I'm going to do 100 confidence intervals of sample size 50. So we did 100 intervals, and if we count them, there are 7 green ones there, right? So out of every 100, out of the 100 intervals that we did, 93 of them captured P. Okay, 93 of them have the red line going through them, but 7 of them don't. Okay, and that's what this whole thing. You see this confidence level down there? That's what confidence level is all about. Okay, here's what confidence level means. For a 90% confidence interval, for every 100 samples that we do, or however many samples we do, we expect 90% of our intervals to capture P. What it doesn't mean is there's a 90% probability that P is in there. That's not what it means. It means that for every 100 confidence intervals that we do, we expect 90 of them to capture P. Now you're going to say, well, Mr. O'Neill, on your applet, 93 out of 100, that's 93%. Again, if I was to continue to do this, okay, I would get about 90%. Okay, so let's do it again. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this time 89% of our applets, 89% of our intervals captured P. Okay. So what would 95% do then? What happened? If I go from 90% to 95%, we get wider intervals. So more of them, since they're wider, okay, more of them are going to capture P. So what's the difference between a 90% confidence level and a 95% confidence level? Okay, in a 90% confidence level, we expect 90% of the intervals to capture P. Actually, 89 of them do. In a 95% confidence interval, what do we expect to happen? We expect 95 out of 100 intervals that we create based on different samples of the same size. Our sample size is 50 here. All of our samples have an n size of 50. We expect 95% of our intervals to capture P. In this case, it was 96 out of 100. So what would 99% do to our intervals? It'd make them wider. In this case, every single one did. We had 100 out of 100. Okay, but we would expect, look at this one right here is close. Okay, we would expect 99% of our confidence intervals based on 100 different samples of the same size. We expect 99 of them to capture P. Okay? Okay. So, next thing I want to talk about. We do, let's do 90% confidence intervals. We did 100 of them. Okay, so what's our parameter here? Our parameter is still 0.49. Okay, so let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. Okay, so 88 of them captured P. What happens if I double my sample size? Okay. Well, let me see if this will work. No, it won't work. Okay. So I got a, I have an n size of 50. Okay. And let's do 100 confidence intervals. What happens if we now double our sample size to 100? Do you see what's happening to the intervals? Now, did that change the confidence level? Do we still expect 90% to capture P? Sure we do. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 didn't. 91 out of the 100 did. So that doesn't change the confidence level, but what did it do? Well, if you noticed, it changed the size of your interval. When you went to larger samples, what happened? You got narrower intervals. Why'd you get narrower intervals? You got narrower intervals. Look at where the middles of all these are. What does that mean? The middles of these are closer together. So what does that mean? Well, it means that there's less variation from sample to sample. So what happens if we double the sample size again? We're going to go from 100 to 200. We're going to create 100. Look at that. Now we got even narrower intervals. Doesn't change the fact that we expect 90% of our intervals to capture P. I think that time it did come out to exactly 90. Okay? But as our sample size goes up, our variation decreases, hence we get narrower and narrower intervals. Okay? Now, mathematically, why that works out is because in your confidence interval formula that you have, where you have p hat plus or minus z times the square root of p hat q hat over n, what I'm doing is I'm changing the n size. So when I make n bigger and it's on the bottom of a fraction, it actually makes your intervals smaller because you're dividing by a larger number. Okay? So our sample size narrows our intervals, okay, because variation will decrease. Okay. I think this is the same deal. Okay, all that this is showing 95% confidence interval. In a 90% confidence interval, okay, all this is showing 94% of them got hit. That these red dots that are in the middle are your actual p hats. The green line represents what p is. Okay, so that's basically showing the exact same thing that we just looked at. Okay. All right, so in going back to this applet, just showing you the same thing. I just want you to see it in terms of the distribution. If I do 100, let's do 100 samples of an n size of 50 where our p-value is 0.5. Here's what our distribution will look like. That's what our sample distribution looks like. So most of our samples, let me see if this shows up. Okay, so this what I just clicked on represents, let's see. represents the interval that's lighting up. Okay, so most of these have a center at 0.5. Okay, but these out here, these red blocks represent the intervals that did not capture P. Okay, so that's this one right here. So this interval, let's see, this has a let's see, this has a p-value that's below 0.7, so it looks like it's maybe 0.66, 0.67. Okay, and this interval goes from 0.529 to 0.791, and our p-value is 0.5, so it did not capture. It did not capture our p-value. Now, if we change the n size, okay, and we're going to change it to 100, let's watch what happens to our distribution. Okay, our distribution, what happened now is the variation decreased. Okay, and we're doing a confidence interval of 95%. Actually, 98 of them captured P. Okay, so our variation wasn't in our last distribution was like in the 0.3s to almost 0.7. Well, this one goes from above 0.4 to below 0.6. So we have less variation in our sample distribution. Hence, that's why these intervals are not as wide. And then we'll increase it again. Oh, not 200 intervals. We want 200. We want sample sizes of 200 now. So watch what happens again. Watch what happens to the distribution, and then we'll watch what happens to your intervals. So let's do that. And okay, so what happened is we got even less variation. This goes from inside of 0.42 to not much less variation, but we definitely do have a little bit less variation. And you notice that your intervals got even narrower. Okay, and then I'll just do one more. Let's go from 200 to 400. And okay, well, we wound up getting a little bit of variation here, but notice how narrow your confidence intervals are, okay, compared to as we increased our sample size. Okay, we got these here that looks like they're around, I don't know, maybe 0.449, so p hat of 0.405, and this is a p hat of 0.422. So but you notice that as our sample size increases, we're getting less variation. These black dots are getting less variation in them, and hence we're getting narrower and narrower intervals based upon that. Okay, so that's going to lead us into our next section about interpreting confidence intervals. Alright, so let's go into the interpretations here. So I'm going to just start with what we just talked about. Now, there's two interpretations we have. We have interpreting the interval itself, and we have interpreting the level. So since we just did the applet, let's talk about the level. So a 95% confidence level means that in 95 out of 100, or 95% of all samples that we do of the same n size, we expect to capture P. A 90% confidence level means that in 9 out of 10 or 90 out of 100, or 90% of all samples of the same size, we expect to capture P. So we saw on the applet, because of the natural variation that exists from sample to sample, okay, that sometimes we get a sample where the statistic, our p hat, is so far away from our parameter, in this case p, that the interval doesn't even capture it. Doesn't mean we did anything wrong. It just means that, you know, if we get a sample and our p-value is 50% and we get a p hat of 79%, we're pretty far away from our actual p-value, so our interval may not capture that. Okay, so that's what the confidence level means. It means that that's the percent of samples that we expect to capture P. Now, the interpretation of the interval itself A 95% confidence interval means that we are 95% certain. Now, if we're 95% certain, that is not a probability. Okay? We're quantifying our certainty. It doesn't mean that there's a 95% chance that P is in the interval. That's not what it means. Okay? It means that we are 95% confident that P is in our interval. Okay? Either P's either in the interval or it's not. Okay, it's not a chance that it could be and a chance that it's not. Okay, it's what we're doing is we're quantifying our certainty. Okay, how confident we are that P is in that interval. For example, if we have a confidence interval that is 0.2 plus or minus 0.05, this means that we are 95% confident that the true proportion, or P, is, well, 0.2 minus 0.05 is 0.15, and 0.2 plus 0.05 is 0.25. So we're 95% confident that P is in between the lower bound of 0.15 and the upper bound of 0.25. Yeah? So that's how we interpret our confidence interval. And we always interpret the confidence interval basically when we do this part S. Okay, when we state our conclusion in context, that is the interpretation of the interval. Now, if they ask you a follow-up question and they say, what does the level mean? That's the percent of samples that we expect to capture P. So the larger the percent in the confidence interval, the more certain we capture P, but with less precision. So it's always certainty versus precision. Okay, the more certain we are, if we're 99% confident, then we're going to have a wider interval, so we're going to be less precise as to where P is. Okay, the lower the percent in the confidence interval, the less likely we capture P, but with more precision. So we got a narrower interval. Okay, so we've narrowed down where the interval is, where we've captured P, so we've tried to be more precise about it, but now we're less certain. Okay, so we trade certainty for precision. So again, this whole thing down here, watch out. A 90% confidence interval does not mean, there's a 90% chance we captured P. We either captured P or we didn't. It's that simple. What it does mean is that if we did multiple samples of the same size, we expect to capture P 90% of the time, or 9 times out of every 10 samples. So here is what a based upon, let's do some different confidence intervals. We do that. We got all these different confidence intervals that are about the same size. 8, 9, and then 10. Okay? And 9 out of 10 of them captured P, which is the heavy black line. Well, this one didn't. Okay? It doesn't mean we did anything wrong. It's just that the P hat came out well below, because this would be below, well below what the P value is, and our interval didn't happen to capture P this time. Okay? So that's what happens. So if we did a 95% confidence interval, then if we did 100 of these, we'd expect 95 of them to cross the line and 5 of them not to. Alright, so example 3 here. Let's take a look at this. Alright, so what sample size is needed in a follow-up study if we want a margin of error of 5% with 90% confidence? Okay, so we know in our confidence interval formula that this part right here is margin of error. So we want 5% to equal our margin of error. Well, we know in our margin of error, a 90% confidence interval has a z of 1.645. And in a study, we had 27% reported improvement, so that's P hat So Q hat must be 0.73. And we don't know what N is. Because what sample size? Well, what are we looking for? We're looking for N. So we got to do a little bit of math here. So we got to divide 0.05 by 1.645. And then we got to square it. So this is 0.000924 equals, let's 0.27 times 0.73 is 0.1971 over N. And then we multiply N by both sides. And then we got to divide by 0.000924. Okay. So we got to divide 0.1971 by 0.000924. And we get 213.31. Now, remember, you're doing a sample, so you can't have 213.31 people. So usually it's safest to round up, because if you have under 213.31, okay, then your margin of error might be just below 5%. So it's safer to say approximately 214. Okay. All right. Now the next one, 98% confidence. Okay. So whenever you have a confidence interval and you don't know the Z, draw a picture. So here's what you're going to do. You know that you got P hat here, and you know you got an interval. And in that interval, you've captured the middle 98% of the distribution. Well, if I've captured 98%, what part haven't I captured? The answer is 2%. And if you notice in your interval, that 2% is split between this region here and this region here. So that must mean that there's 1% left in this tail and 1% left in that tail. Well, if there's 1% left in each tail, then what percentile does your confidence interval begin and start at? Well, it begins at the first percentile and it ends at the 99th percentile. So in order to get a Z-score, we got to go into second distribution and we do inverse norm. And we can do either 0.01 or 0.99. Either one is fine. And we get 2.326. Now if I did 0.01, I would have gotten negative 2.326 because it's equidistant from the mean. So what we got is 0.05 equals 2.326 square root of 0.27 times 0.73. Okay. Over N. So what we're going to wind up with is 0.05 divided by 2.326, square it, and we get 0.0004628 equals 0.27 times 0.73 is 0.1971 over N. Multiply both sides by N. Then we're going to divide 0.1971 divided by this answer that we just got. Okay, and we get 426.54. So N is going to equal approximately 427. Okay. Okay, so I believe that concludes this chapter, other than the problems that we haven't done in the packet, which we'll do in class.